Hello, I am Akshay and I am presenting a paper on source-free domain adaptive semantic segmentation. Unsupervised domain adaptation aims to transfer knowledge from labeled source to unlabeled target, overcoming the domain shift. However, conventional domain adaptation techniques assume simultaneous access to both domains. Source-free DA relaxes this assumption in a vendor-client setting. The vendor has access to a labeled dataset, enabling a supervised model. Conversely, the client has access to unlabeled target data for which they require a target-specific model to be deployed in a similar scenario. However, vendor and client cannot share their data due to privacy or profit concerns, but vendor may share a source model with the client who needs to perform source-free target adaptation. For this practical setting, we propose generalize then adapt, where vendor and client adopt cooperative strategies. The vendor aims for a generalized source model to serve a wide range of clients. The client aims to utilize the shared source model towards an effective target specific model. First, we ask how can a vendor serve multiple clients with a single model? Motivated by multi source DA works utilizing multiple source domains for target generalization, we cast vendor side as a multi source learning problem. For clarity, we briefly discuss hypothesis supports. We train a multi head model with multiple sources. For any target, the expected error of the first head is the average loss over target samples. Here, H is a hypothesis or classifier from a subspace H1, which is a subset of the hypothesis space A. Similarly, for the second head, H comes from a subspace H2. For any head, the hypothesis will be confined to a particular subspace. Ideally, the hypothesis with minimum target error could be found, but in this case, H2 best supports the target being closest to the ideal hypothesis. In short, hypothesis support indicates the extent of support exhibited by a model for any input. Now we seek potential hypothesis support configurations which are distinct ways to use multiple sources. First is empirical risk minimization, where a single hypothesis is trained using all domains. Next, we consider a set of domain expert hypotheses, that is, each trained with data from one specific domain. We also consider a set of leave one out hypotheses, each trained on all except one specific domain. To complement the domain specificity of domain experts and leave one out, we add domain generic ERM to obtain DE++ and LO++. Now we assess these supports over various targets. For the triangular target, LO is the closest and thus a suitable support for adaptation. For the square target, another LO support is closer than ERM and domain experts. For the plus-shaped target, the DE support is closest, while LO is a close second. Next, for the star-shaped target, LO again proves better. The pentagonal target is closest to ERM, while LO is not far. Finally, for the heart-shaped target, LO is again the closest. Hence, leave one out plus plus reasonably supports most target scenarios, highlighting its suitability for the vendor. Next, the major question is how can the vendor obtain multi-source data? Since annotating multiple domains is expensive and time-consuming, we use diverse label-preserving augmentations to simulate multiple sources. Moving to the vendor-side approach, we use the insights to propose SOMAN, a multi-head network based on LO++. The global head is trained as ERM, while the kth leave one out head is trained using all except the kth domain. SOMAN may lack inductive bias or a scene prior for semantic segmentation. This leads to merged and splitted region problems as the network fails to model plausible segments. To combat such spatial irregularities, we propose a prior enforcing autoencoder conditioned on domain generic features. It is trained to align the output distribution with the source label distribution. Next, we move to the client side where source-free adaptation is performed. As the vendor shares the SOMAN, the client can choose the optimal head that suits their specific target data. We propose to use the head K dash with the lowest average self-entropy or the most confidence on the target dataset. Using the optimal head K dash and the CPAE, we extract reliable pseudo-labels via confidence thresholding. Next, we use the pseudo-labels for self-training but update only the backbone to preserve the task knowledge of the classifier. Now we show the key results of our work. Our vendor-side approach results in improved domain generalization. We also evaluate domain adaptation, comparing with both source-free and non-source-free methods. Despite the source-free restriction, we outperform even non-source-free prior arts. Qualitative results show that vendor side is better than single source, while CPA structurally regularizes the predictions and reduces merged and splitted region problems. Summing up, we focus on source-free DA for segmentation in a vendor-client paradigm. Vendor has labeled data and client has unlabeled data with restricted data sharing. The vendor trains a model and shares it with the client. For this, we propose a generalized strategy for the vendor followed by model sharing and a source-free adapt strategy for the client. Please refer to our paper and project page for more details. Thank you.